Yay. All right, here we go. All right. Well, thanks everybody. Welcome to the June our Govys event. We're really excited to have Joe Schafer here from the Census Bureau. He's given a talk for us before on one of the other packages, our packages that he's written. And I will let him introduce himself on the topic for today and the new package, I think it is that he's written. But just a little housekeeping. Joe has sent the slides to me, and so I will share them with registered attendees afterwards. And so you'll get those. Also, we will be posting this to our YouTube channel. I will just do a little plug for July. We have a July event scheduled already. That's also at a different day and time. It's on the Tuesday. Donna, correct me if I'm wrong, but I think it's July 16th at 11 a.m. So that's a bit different. Our speaker's in the UK, so we want to adjust the time to suit his schedule. And we're having Robin Lineker, who is the developer of Splink, which does record linkage. It's actually a Python package, but even though we love R, we're open to other tools, of course. And so he will talk a little bit about R and record linkage. And Donna, you put that in the chat. Yay, thank you. She's always on top of things. And we have Q&A. The Q&A feature is enabled. You can put questions in the chat. Joe will take questions as we go, so we'll monitor that for him. And also Donna said that if you would really like to say something, that you could, I guess, raise your hand and she will promote you to actually speak and not put something in chat or something. All right, so without further ado, I'm going to pass it to you, Joe, and let you tell us about your package.
Okay. All right.
And I do see it, so it's good.
Great. Okay. So thank you for coming. My name is Joe Schafer. I work at the Census Bureau and I do a lot of modeling and a lot of coding. And I'm going to be talking today about predictive latent class modeling, give some background motivation, discuss some applications, and then focus on the software, which is actually a work in progress, but we are making progress. And as Wendy said, I'm happy to take questions. If you interrupt me with a short question, I'll be very happy to respond. I have a hard time monitoring the chat box while I'm speaking, so I'm be very happy to have you raise your hand and just interrupt me verbally. But as Wendy said, if you raise your hand, I think you're all muted until she unmutes you. But I'm happy to interject if the question is it'll have to wait till the end of the talk or later in the talk. I'll get to that. I'll just say that. So this is what I'm going to talk about, and I will just get right to it. Okay. So descriptive latent class models. Descriptive latent class models are what you could call traditional or classic latent class models. They've been around quite a long time. They were originally developed back in the 1970s. I think the first article about them appeared in the 60s, actually. It wasn't until the 70s and 80s that we could actually fit them. And they were developed in the social and behavioral sciences and later used in education, biostat, medicine, and a bunch of other places. The idea is quite simple. You've got some variables y1 to yj that you can observe, and you want to model their distribution. In fact, you want to model especially the associations among them. And so the way you do it is you say that they are conditionally independent given a latent variable that we call z. Latent means you can't see it. but you're acting as though it exists and it's there. And this is a categorical variable taking possible values 1, 2, up to capital K. So Z is what I'm going to be using for the latent class variable, and capital K is the number of classes, and capital J is the number of items. So this looks a little bit like a factor analysis model, except with factor analysis, the Y's are continuous and normally distributed, and the Z is also continuous and normally distributed. This is it's an example of what we call a finite mixture model. A finite mixture model says the distribution of the items that you see are a mixture or a weighted sum of independence models. And the weights are called, I call them phi sub k. That's the probability that that latent variable Z takes the value k. And since it's not observed, you actually say that the joint distribution of the Y's is equal to the joint distribution given k times the probability of k summed over k. So that's where this formula comes from. So this is the joint distribution of the observed variables. These phi's, phi 1 through phi k, I'm going to call them class prevalences. They indicate, the probabilities that a randomly chosen unit from the population falls into class 1 up to capital K. So there's a vector of class prevalences. And then the individual items have what we call item response parameters that vary by the class. So every item, yj, has a theta for the particular class. So there's an array of item response parameters as well. So that phi and the theta together are unknown parameters. Now, these item response distributions are typically categorical. That's the classic latent class analysis. But you can also do this very easily with any regular exponential family distribution, such as a normal Poisson. These are all very common. And these are also extremely easy to fit if you use the EM algorithm. And EM treats the latent class variables as though they're missing data. So as far as I know, this was first written about by Leo Goodman in 1974. That actually predates the EM algorithm paper, which came out in 77. So this latent class models actually predate EM. The E step of EM is very simple. What you do is you go through your sample units, and for each one, you compute the posterior probability that it falls into each of the class given the items that you see. And so this is just Bayes' theorem. You just apply Bayes' theorem to get these posterior probabilities, and then you re-estimate the parameters phi and theta by fractionally distributing each of the responses across classes 1 through k using these probabilities that you computed in the E step. So that's like just a weighted estimation for both the phi and the theta. So with exponential families, these are extremely easy to do in the M step, and the E step is also pretty quick. So the interpretation of these models is really been the key to descriptive modeling. So descriptive LC models, we really care about the interpretation, and that the number of latent classes is often chosen by the analyst based on fit and also interpretability, or some mixture of the two. The interpretation of the classes comes from those estimated item response parameters. So by looking at those item response parameters, and you can see, well, sort of what the typical members of that class are. And then you look at it from class to class, and then you understand what the classes mean. An interesting thing about these models is the likelihood is invariant to arbitrary reordering of the class labels. So depending on where you start, the EM algorithm can converge to any one of k factorial equivalent solutions. And of course, if you just look at the solution, you can permute the class labels any way you want. And it's the same, it implies the same distribution of the observed items. Now, it's also interesting that sometimes minor modes and non-identifiable situations are also common, especially as the models become more complicated. So I'm going to leave that aside for a moment. We will return to that later. Computationally, these models are very attractive for a number of reasons. First is that the model fitting time turns out to be roughly linear in the number of observations, the number of classes, and the number of variables, which is really surprising because how often do you see a multivariate model where you get linear in the number of variables? Usually it's cubic in the number of variables. So they're very scalable. And another nice thing about these is that there's no need to create the full J+1 dimensional frequency table. So if we have categorical items, the Ys are all categorical, we can think of every observation as falling into a cell of the J-dimensional frequency table, and then you can add another dimension for the latent class variable Z. But you don't actually have to work with that full dimensional frequency table, which makes it computationally very attractive for when you get large numbers of variables. The number of cells in that table would just explode, but you never actually need to enumerate them all. Another interesting thing is that missing items don't complicate the model fit at all. You just skip over the missing items in the E step and the M step. So it's actually easier, quicker to fit it with missing data than it is with observed data, with fully observed data. So that's another nice feature. You can also do Markov chain Monte Carlo. That's about as easy as the EM algorithm. And interestingly, you can get the class labels permuting during a run. So you've got to be careful if you're interpreting the classes. And now there is an interesting relationship to log linear models. It turns out that these are a special case of log linear models with incomplete data, and that is log linear if you consider Z to be part of the variable system. They're not log linear for just the Ys, but if you include Z, then they become a conditional independence model, which is a log linear model. And if you have software that's capable of fitting log linear models with missing data, and if your software can accommodate variables that are completely missing, then you can also do it with log linear modeling. But the log linear implementations are slower and they require a lot more memory because they are iterating over that full frequency table, including the empty cells, in which you often have a lot of. I'll just very quickly mention that there have been some applications of these latent class models at the Census Bureau and at other agencies, mainly in the realm of response error modeling and prediction and imputation from multi-source data. For the interest in time, I'll just skip over that now, and I'll go on to the predictive models. So I have been talking about descriptive models where the meaning of the classes matters. In the late 2000s, Jeroen Vermunt from the Netherlands proposed using latent class models with large numbers of classes, and he wanted to use them for multiple imputation of missing values in data sets where you have potentially large numbers of categorical variables. And that proposal spawned a series of papers by him and a student or postdoc, Vidodo, and a few others. And so there's an interesting line of publications coming out of that group using these predictive latent class models, which are class models with large K, mostly as a multiple imputation engine. These are predictive because the latent classes are not really the main interest. The reason for doing this is for getting a good summary of the joint distribution of the Ys for purposes of imputing the missing values given the observed ones. You can think of these models as being non-parametric in the sense that any joint distribution for a set of categorical variables can be exactly represented by a latent class model with a finite number of classes. It's kind of a stunning result. no matter how complicated the joint distribution over that frequency table, observed frequency table is, you can represent it exactly by a latent class model with a finite number of latent classes, which means that as you increase the number of classes, you can fit the observed distribution, including all associations that may be present, arbitrarily well. And this also gives rise to an idea for Bayesian model selection, where instead of fixing the number of classes a priori, you apply some sort of prior distribution, such as a Dirichlet process prior to the class probabilities, and you run Markov chain Monte Carlo and allow the data to choose the number of classes interactively. So the usual way of doing this is called the Dirichlet process prior. And in this Dirichlet process prior, you can think of those class prevalences as being an infinite sequence. So there's an infinite number of classes, countably infinite, because you can count them, 1, 2, up to whatever, and just keep going. And you represent each of the class probabilities as the product of a beta random variable times 1 minus all of the betas that came before it. And so this is actually a stick breaking process. You can think of taking a stick of total length 1, and then using a beta distribution, you decide where along the stick you're going to break it. You take the length of the left-hand piece as your first class probability, and then the remainder, the right-hand piece, you then rescale to 1 and you break it again. And you can keep breaking that stick and ad infinitum and get an infinite number of class probabilities that sum to 1. And the typical way of doing this is to call it a beta distribution with parameters 1 and alpha, and call alpha, but put a gamma distribution on that alpha. Now, you don't actually have to go out to an infinite number to get a good model. Jerry Reiter's group started to use these and proposed truncating the process at some large value that we call Kmax. So we just take, after breaking the stick a certain number of times, you just take the whole remainder and throw it into the last class, and then you stop breaking it. So you pick a Kmax that's pretty large, larger than you think you need, and then you just forget about everything after that, and it becomes a truncated process. But you still apply this Dirichlet process prior to the rest of it, which tends to give you a set of probabilities that dampen the last few classes, so that you get most of the probability concentrated on the initial classes. This is an alternative to the traditional Dirichlet prior that could also be used for fixed K. Interestingly, with these predictive models, if you're running Markov chain Monte Carlo, whether you're using the Dirichlet process or not, you can get label switching, but that's not a problem for these models because you don't really care about the latent classes. All you care about is representing the joint distribution of the Ys, which will then imply the distribution, the conditional distribution of any set of them given the others. So even if the labels are switching, the predictive distributions for imputing the missing values are not changing at all. Too many classes are not a problem either. What happens is unnecessary classes become empty during the Markov chain Monte Carlo run. So during Markov chain Monte Carlo, what you're doing is you're drawing latent classes for all of the observations under a current set of parameters. And then given those latent classes, you're drawing new parameters from their conditional posterior distribution, and you go back and forth. If you have unnecessary classes, if your Kmax is too big, the only thing that's going to happen is some of those classes will be empty during the Markov chain Monte Carlo run. And so you can actually monitor how many empty classes there are and how many non-empty classes there are. And that can give you an idea of whether you can trim your Kmax and make it smaller and save some computation. Now, underfitting can be an issue. If the number of classes is too small, then the model may fail to capture some important features of the joint distribution. So if you're going to err on the side of overfitting or underfitting, it's better to overfit, because the only danger there is not that the model becomes unstable, but it just takes a little bit longer. You're doing a bit of unnecessary computation, and that's it. So the main question I care about is, do these models actually work? And I will give a qualified yes as my answer. I have been finding that these have pretty good performance. Certainly, they're more convenient, and they tend to work better than their competitors. So here's a quick experiment that helped to convince me that these models are working pretty well. So I needed a data set. So what I did was I pulled some tract level statistics. These are summaries of census tracts that are part of the Census Bureau's planning database, which is updated every year. I took the 2022 planning database, which is the first one that used the 2020 decennial geography. So the tracts are the same as they are in the 2020 census. I pulled out just the census tracts for Pennsylvania because I'm familiar with Pennsylvania. It's where I live. And I wanted to be able to look at the data and understand it a little bit better. So tracts tend to have about a few thousand people in them. I pulled out 11 variables based on American Community Survey 5-year estimates. These were continuous variables describing the tract, but to keep things simple, I broke them up into categories, 2 or 3 categories each. And so this is a list of the variables. I won't go into any more detail on what they are. You can pretty much tell what they are by looking at them. Now, with these 11 variables, you can think of it as an 11-dimensional frequency table with about 35,000 cells. And with only 3,400 observations, you can imagine that a lot of those cells are empty. In fact, only 2,000 of them are non-empty, which means that most of that full frequency table is filled with zeros. Fortunately, Latent-Class modeling just skips over them. It doesn't ever enumerate them. It just works with the data that you see. So I decided to model these 11 variables jointly using 2 different approaches. First, I tried fitting a sequence of Latent-Class models, starting with one class, which is an independence model. Obviously, that wouldn't fit. But then I increased it to 2 up to 15. I fit with an EM algorithm using an experimental R package that I'm going to describe in a moment, using my laptop computer. And for comparison, I also fit a sequence of log linear models to that full 11-dimensional table. And for that, I used another R package that I wrote a couple of years ago on the same laptop. And I started with the independence model, and that actually coincides with the Latent-Class model with one class. And then I added all 2-way associations, all 3-way associations. And then by the time I tried to add all 4-way associations, it stopped working because the number of parameters greatly exceeded the number of cells in the table. So here's just a quick summary of how long it took on my laptop. So I mentioned to you that it's linear in the number of classes. So the Latent-Class models fit very, very quickly, except when by the time I got to 15, the time increased quite a bit. And that's because by that time, some of the latent classes were so similar to each other that the EM algorithm had a hard time distinguishing among them. And so the convergence slowed down, and it took a lot more iterations to converge. In contrast, the log linear models took a very long time. The 3-way association model took 817 seconds, and the 4-way I couldn't fit. Here is just a quick summary of model fit statistics. For simplicity, I just decided to look at the AIC, which is a penalized log likelihood. It's not the greatest, but it's something you can compute quickly, and it gets the point across. So what I'm showing you on this plot are the horizontal axis is the number of estimated parameters in the model. And I put it on a logarithmic scale because the number of parameters is increasing pretty rapidly with the log linear models. The y-axis is the fit criterion, and smaller is better. So the red line is the fit statistics for the sequence of latent class models, and the blue is for the sequence of log linear models. The two models coincide for the independence model. And then as you add classes, the fit of the latent class models improves dramatically. The fit of the log linear models also improves when you include all two-way associations, but once you get to three-way associations, it gets worse. And the number of parameters is much, much bigger. So this is just a quick demonstration of the advantage of using these models as opposed to alternatives. With latent class models, model selection is not determined by deciding which associations to include or not. All you do is you set the number of classes and go on. So the model selection is extremely simple.
Hey, Joe.
Sure.
Yes, Wendy. So whenever I see a little plot like that, I think of, like looking for like the elbow and the curve.
Right.
And so if I'm interpreting this correctly, you could use that to, like you said, determine the complexity of the model or the number of parameters.
Yeah, so this plot is suggesting to me that once the number of latent classes is over 10, that they're fitting about the same. Actually, if you looked at another criterion like BIC, that would penalize you more for model parameters, and so then it would start to jump up after about 10, 11 classes. But this is suggesting that you're getting pretty good fit once you get 10 classes. And then what you can do if you move over to the Bayesian world, you start running MCMC, you put on the Dirichlet process prior. What you could do is say set the Kmax to about 20 classes and then monitor how many classes are filled at each iteration. And I think if you fit this model, you'd see it would top out at about 15, which means that any classes beyond that are just superfluous and you don't need them.
Okay, thank you.
Okay. There are lots and lots of applications of these models that are potentially useful at the Census Bureau and elsewhere. What I am going to focus today on today is the idea of using this as an imputation engine. If you have categorical variables and possibly continuous variables, this is a really convenient way to multiply impute multidimensional data. And I'm also going to talk about multi-level models, which is the last bullet on this slide, which is an extension to situations where the individuals are nested within units at higher levels. So for example, you can have persons nested within housing units, nested within census blocks, nested within census tracts, nested within counties, and so on. It turns out that these models are really quite amenable to multi-level modeling. And I'm going to explain how that works right now. With multi-level models, you imagine that there are multiple levels of data. So you can think of level 1 as being, say, persons, level 2 being housing units, which are collections of persons, level 3 being blocks, which are collections of units, and so on. So capital L is the maximum number of levels that you're considering in your model, or the number of levels you're considering. We assume that we have strict nesting. So each unit at level L belongs to exactly one unit at the next level up. So every unit at each level, you have to know which higher level units it belongs to. At every level, you imagine that there are some observable items or variables. And these variables are different at every level. So characteristics of persons are not the same variables as characteristics of the housing units. So persons, you might have age, sex, race, and ethnicity. Housing units, you might have number of persons in the unit, whether they own or rent the unit, and so on. So each level has its own set of categorical or continuous variables. I'm going to stick with categorical today. And so the items at any level are going to sit in a rectangular data set where the number of rows corresponds to the number of units in that level, and the number of columns corresponds to the number of variables. And you can have missing values in any of these matrices. And you also need identifiers that link each level to the level above it, if there is one, and the level below it, if there is one, just so that the software can understand the units to which each, the higher level units to which each unit belong. Now here's the interesting part. For each unit at any level, there is a latent class variable for that level with possible values whose probabilities depend on latent class variables for all of the higher level units to which that unit belongs. So a little bit hard to understand, but in the persons nested within housing units, nested within blocks, you can think of it this way. You can think of each block as belonging to a latent class that describes the block. And then each housing unit within that block belongs to a latent class that describes the housing unit, and the distribution of those of that housing unit level latent class depends on the block level latent class. So, and then going down to persons, each person has a latent class. The probabilities of falling into those classes depend on the latent class for that housing unit and for the block in which it sits. So there's this hierarchy of latent classes. And now the phi's have this nested structure. The class prevalences have probabilities that depend on the latent classes above it. So I'm not going to belabor this notation. It's a little bit messy. For local independence, we now have two different possibilities in the literature. There's a strong version where the items at any level are conditionally independent of one another, given variables at that level. The items at any level are conditionally independent of one another and variables at other levels, given the latent class at that level. And then there's a weaker version where it depends on the classes at the higher levels as well. There are arguments for and against each of these that you could make. I tend to go with the weaker version, usually by default, but you could also impose the stronger version. So let me just very quickly show you what's happening. If you thought of a generative model for how this works, so if you think of a three-level model where you have a block and then housing units within the block and then persons within the housing unit. Capital L is 3. So at level 3, a housing unit has a latent class variable, which I'm calling Z superscript L, because it's the latent class describing the block. Given that latent class for the block, each housing unit has a latent class, which I'm calling Z superscript capital L minus 1, and its distribution depends on the parent at the higher level. So every housing unit has a latent class who's with probabilities depending on the higher one. And then when you go down to persons, each person in each housing unit has a latent class whose probability depends on both the latent class for the housing unit and for the block. Now that we understand this structure, we start to add items. So the items, at each level, there's a vector of items, and in the stronger version of local independence, the distribution of those items depends only on the latent class at that level, and in the weaker version, it depends on the latent class at all the higher levels. So this can be a little bit mind-boggling, but it does work. Now, there is an interesting way that you can implement the fitting of the multi-level model. This was first described for a two-level model by Jeroen Vermunt in 2008, and I have generalized it to any number of levels. It consists of a bottom-up cycle and then a top-down cycle. And for the sake of time, I'm just going to skip over this. But it is kind of an interesting extension of a latent-class model, model fitting procedure. It's not that much more complicated. And implementing it for any number of classes, or sorry, any number of levels is not hard. Once you do it for two and understand how it generalizes, you can just write the code to do it for any number of levels. Now, I'm going to just briefly mention the software that's out there for latent-class modeling. In terms of commercial packages, the two big ones are called M+ and Latent Gold. These are both commercial. There are some plugin routines for SAS and Stata. The level of support is unclear. There is a package for simple latent-class modeling in R. I wrote a package for log linear modeling that you can adapt as long as you don't have too many variables. And there is a new experimental R package out there that I just found called multilevel LCA that will work for two levels. I don't think it's been published, but I've seen it out there. Now, it's important to note these products were all designed for descriptive modeling, for data sets of small to moderate size, not for predictive modeling with large samples, many variables, and many classes. And so that spawned a new project. And this new project was to create software to serve current and future research projects at the Census Bureau that could benefit from this kind of modeling. And I wanted the software to be free and open source because we are all moving toward open source software. I wanted it to be useful for both descriptive and predictive modeling. I wanted it to be capable of multi-level modeling. I wanted it to be flexible and easy to use by anyone who understands what the model is, but doesn't need to have a great deal of technical expertise about what's going on inside. I wanted it to handle large data sets with many variables, and I wanted it to be fast. And so I started programming in earnest back in December. And to date, I'm happy to report that there is an experimental R package. I'm currently calling it bigLC. And I'm calling this experimental. It's not yet released to CRAN, but it is currently being tested by multiple people within the Bureau, including some who are in this webinar today. So it is circulating. They're finding interesting features. They're finding bugs. They're giving me understanding of what to do to continue the development. The way that it works is you input the variables through a data frame or a list of data frames if you have multi-level data. Missing values could be present at any level. I'm pre and post processing the data in R, but the actual model fitting is implemented in fast Fortran. I'm using an interesting interface to Fortran called .call64. I can talk more about that if you're interested, probably not. This software has no upper limit to the number of observations, variables, classes, or levels. You're only limited by your data and how much memory you have on your computer and how much time you have to fit the model. Another interesting feature is that each of the compute-intensive cycles has been parallelized using OpenMP. So I put in parallel loop statements, and that means that if you have multiple cores available to you, and you probably do, my own Census Bureau laptop has 8 cores available, and if I'm working on our Linux research cluster, a single node has 64 cores available. You can take advantage of all of those cores. And so what that means if you're using 64 cores, something that would take a minute now takes a second, essentially. So it's really, really nice that the speed up is very, very noticeable, especially when you have large numbers of observations. So I'm going to give you a quick preview of what it can do. I'm going to work with a data example. My data example is the summary statistics for the 3,400 tracts in Pennsylvania that I showed you before. This came from the Census Bureau planning database. It's publicly released data, so there's no confidentiality restrictions on the data I'm showing you. But there are some missing values because some observations were suppressed for disclosure avoidance. So there are a few missing values in there. The categorical variables are in a data set that I'm calling df.tract. And because those tracts are nested within 67 counties, I've got another data frame called df county with some additional county level variables. And the tracts are nested within the county, and there's a linking variable that allows you to identify the linkages. So at this point, to show you what the software looks like, I am now going to switch to another document so that you can see exactly what it looks like to use this code. So here, all I'm doing is I'm loading the two data frames. I saved it in a hard save file. So I'm loading it, and I'm attaching the bigLC library, and I'm also attaching a library called Coda, which has some nice diagnostics and plotting routines for looking at the output from Markov chain Monte Carlo. So here's an example of what it looks like to fit a single level model for the tract data. So as I mentioned, the tract data are sitting in a data frame called df.tract. These are the first few lines. You can see that they're all categorical. These have 2 or 3 levels each. And then at the end, there is a identifier called county, which tells you which county it's nested within. So that's not a variable to be modeled. That's a variable that we will use to link it to the county level data set later. But for now, let's just look at the tract level data. Here is a summary of the variables. So if you look at these variables, each one is categorical. It's either 2 levels, no, yes, or 3 levels, low, medium, high. And you can see that there is a smattering of missing values here for some of the smaller tracts, smaller in terms of fewer people, that had to be suppressed for confidentiality reasons. Before fitting a model, you have to decide what variables you want to put into the model, and I'm just going to put all of them in. So you take your variable names and you put them together into a model formula. If you've ever done, say, regression modeling in R, you're familiar with a two-sided formula where you have the outcome variable on the left-hand side of that tilde character, and then all the predictors on the right-hand side. Here, we're modeling the joint distribution of all the variables. So you put them all on the right-hand side, separated by plus signs. And the plus sign just means it's just a separator. So the first thing we're going to do is fit the model by an EM algorithm. And all you have to do for this is give the model formula, which I already saved, tell it the number of classes that you want and the data frame name. And it's a good idea to set the random number generator seed because I use random start values. And so if you want to reproduce it, you should set the seed. Now, after about 3 seconds, it says failed to converge by iteration 1000. So let's look at some results to see what happened there. If you look at the summary, you see the formula, the items, number of observations, number of items, number of parameters, and so on. Says that EM failed to converge by 1,000 steps, but the maximum absolute change in parameters between those last 2 iterations was extremely small. It almost converged. And then if you look at the class prevalences, the estimated class prevalences, you can see what they're like. They've been, here I reordered them from largest to smallest. So you see the largest class comprises about 14% of the population. The second largest is 9%. And then as you go down, you get down below 1%. Now we haven't yet converged, so let's continue to run EM. The way you do it is you take the result and you feed it back into my bigLC function. And what it does is it just continues from where it left off. And now you don't get a lack of convergence message. And if you look at the summary now, you see that EM converged at iteration 451. So that's 451 after the initial 1,000. So it took 1,451 cycles to converge by this criterion. Here's the final log likelihood and the estimated class prevalences, which are essentially the same as what I showed you before because it barely budged. Now let's look at all of the estimated model parameters. So if you use the coef function, you can pull out all of the model parameters. And here, the model parameters are the class prevalences, which I already showed you, but also the item response parameters, which give you the interpretation of what the classes are. So class 1, the largest class, which is about 14% of the population, consists of tracts that are low density, essentially with probability 1. So these are rural tracts. They have low percentages of Hispanics, very high percentages of whites, low percentages of blacks, and so on. Sort of moderate percentages of vacant units, and so on. So that's the dominant, the most dominant class. The next class is quite different. The next class tends to be higher density. So these are more suburban and urban. They are very high Hispanic and very low white and quite high black. The next class is high density, so urban blocks, medium levels of Hispanics, low levels of whites, but very high levels of black. So these are predominantly urban high black tracts. And so on. I truncated it after class 4 because after that, there's 30 classes in this model, and some of them are quite sparse. They're almost empty. Okay. The next thing I'm going to do is run Markov chain Monte Carlo, and I'm going to start from the estimates that EM gave us. So doing this is very easy. You just take the result from EM, you feed it to the bigLC function again, and you change the method to MCMC. That's all you do. And then by default, what happens is it runs 1,000 iterations of Markov chain Monte Carlo, and then it reports the simulated class prevalences at the end. So these are no longer the maximum likelihood estimates of the prevalences. These are now a random draw of the class prevalences from their Bayesian posterior distribution. They look pretty similar, but now instead of using maximum likelihood, we have now applied this Dirichlet process prior, which is going to tend to dampen the probabilities in the smaller classes. So they're similar, but the probabilities die off more quickly. One more thing that we're getting here is imputed class frequency. So at the very end, it saves the last set of imputed classes for all of the observations. And you can see how many observations were imputed to fall into class 1, how many fell into class 2, and so on. You can see that a lot of these classes are empty, which suggests that we didn't need to use 30. 30 is overkill. And so we will think about that. Let's look at some other diagnostics. So here, what I'm plotting is this is a trace plot of the log likelihood. So if you remember, I started at the ML estimate. So I started at the mode. So the log likelihood is the highest at the starting value. As you wander away from that, as you wander through the posterior distribution, the log likelihood drops off pretty quickly, and then it settles down. And this is what it looks like. I continued for another 5,000 iterations and then did another trace plot. And this is what it looks like after 5,000. So this is what you would call a slowly converging or slowly mixing chain. takes, if you look at the autocorrelation, takes quite a long time for the autocorrelations to die down, which is not, which is tends to be the case with these models. Now, another summary that I like to examine is called the non-empty class series. This reports the number of non-empty classes at each cycle of MCMC. And this helps you to diagnose whether Kmax should be increased or decreased. So if you remember, I set the maximum to 30, but as you look across these iterations, the number of classes that are actually occupied tends to be below 25 most of the time. Every once in a while, it jumps up to about 27, 28, but it never gets to 30. So we do have enough classes. Now I'm going to take that result and use it to impute the missing values. So as I mentioned, there were a few missing values in that data set. If you take the result from Markov chain Monte Carlo and wrap it with the function impute items, it produces a single random imputation conditional on the parameters held in that final MCMC object. And so you can think of these as this data set is one imputed data set for purposes of multiple imputation. It's a draw from the posterior predictive distribution of the missing data given the observed data. And if you look at it, there's no more missing values. All of the NAs were filled in. Another interesting thing is that there is a latent class variable included in that imputed data set. So you can see what the latent classes were that each census tract in this case was assigned to. And then if you start subsetting the data set by classes, you can get a good understanding of what the latent classes are like. So here, what I'm doing is I'm pulling out that first class, class 1, looking at a summary of that part of the data set. You see that these are low density tracts. So these are rural tracts, very high proportion of whites, low minority districts or low minority tracts with, turns out, quite a bit of vacancy. The second class, these are high density tracts, high Hispanic, high Black, low white, and pretty high number of vacancies, pretty high vacancy. You could continue with any of the others. Just to wrap up, I'm going to now show you how easy it is to fit a two-level model. So I mentioned before that there's a second data frame here called df.county. This has only 67 observations, one for every county. There's a couple of variables in there. One is a classification of the urbanization level of that county, comes from the National Center for Health Statistics. And then there's the number of tracts, which you can treat as a county level variable. And then there's the county identifier. This county identifier is the variable that is going to link this to the tract level data set. So now to supply the data, you take those two data sets, the level 1 and level 2, and you put them together into a list. And then you specify a formula. The formula has 3 parts. The parts are separated by these vertical bars. The first part lists the variables from level 1 that you want in the model. The last part lists the variables you want from level 2 in the model. And the middle part is the variable, the name of the variable that provides the linkage. You can also fit a 2-level model without any level 2 variables. And you just put in a constant 1 like this. And that's often sensible to do that if you want to just form clusters based on the latent classes at level 1, or look at clustering based on that. I'm going to just very quickly show you how to fit the model now. At this point, you specify the formula, as I mentioned before. You provide a list of data frames, and the Kmax is now a vector, giving you the maximum number of classes at level 1 and the maximum number of classes at level 2. And then away you go. For the sake of time, I'm going to stop here And I will go back to my last slide, which is some ongoing work. And this is not really that important to go into now. It's just important to know that we are actively developing this and trying to add enough bells and whistles to handle the kinds of difficult problems that you see at the Census Bureau, and I'm sure at your agency as well. I have all of the references here if you're interested, and at this point, I'm happy to take questions.
Great, thank you, Joe. That was very, very thought-provoking. And this is like sort of the second time I've heard it, and I think I'm understanding it better. So that's good. We do have one question in the Q&A. Dimitri asked, did you test your package on synthetic data that you know the underlying generative process for?
Short answer is yes, in small examples. The more involved answer is my impute items function currently imputes the missing data, but keeps the conditional on the observed data in the data set. With a very little tweak, I can expand it to impute synthetic data to create a full synthetic data set. And that's going to make it really, really easy to do that kind of validation work. So what you do is you can fit a latent class model to a real data set, get the estimated parameters, use those estimated parameters to generate synthetic data from that distribution, fixing the parameters, and then and it becomes like a parametric bootstrap, and you can look at the repeated sampling properties of your estimates. And so that's certainly something that is very worthwhile and important to do. Is models like this can be pretty complicated, and you only understand how well they perform when you start to do things like that.
Yeah, thank you. So if I'm, oh, okay, sorry, the question disappeared. So if I'm understanding this correctly, is this essentially what you were showing us? I mean, it seems like it's equivalent to clustering, unsupervised learning. Am I understanding that correctly?
You can think of it that way. It's a parametric kind of clustering. And there are certainly lots of clustering models that are rooted in a latent class analysis.
Yeah, because I think some of the work that's done in text analysis uses the latent
exactly. Latent Dirichlet
topic modeling.
Right, right.
Okay, I think you and I need to talk like offline or something.
Okay.
Because I'm seeing some connections with other work that I'm doing and other approaches for this idea of like nested levels.
Right.
And the work that I'm talking about was sort of couched in a little bit different terms, but I think it's similar when you really look at it. But sort of the explanation of it, I guess, is slightly different.
Yeah, so I can imagine. So if you create a data set where the rows are documents and the columns are say scores on various topics. So whether a topic is appears at a low rate, medium rate, or high rate, or something like that, you can categorize it. Would probably be easiest to start, or whether the topic is absent or present. You can feed that into this software and do latent class analysis. And you apply that prior, and you can the Dirichlet process prior, and you can get sort of a model selected number of different types of documents that exist. And then you can, if you wanted to collect those documents into, I don't know what the documents are, if they're like chapters nested within books, you could then fit a two level model where you can have at that second level some descriptors of the book, whether you can whether it's fiction or nonfiction or whatever, or you don't even have to have any. And then you can, what's going to happen then is the types of documents, the latent classes at level 2 are then going to be used to sort of cluster together or to describe. They're going to the level 1 clusters are going to be used to identify clusters of the at level 2. If you understand what I mean. So you're then getting latent classes of books that have of different types, and each type has its own distribution of latent classes of the chapters.
Okay, we definitely have to talk.
Okay.
Yeah, I'll have to give you like a little presentation on the other method and sort of the framework. But I think there's definitely some synergy that could happen here.
Sure.
So yeah, great, fantastic. Any other questions? I don't see hands being raised or things in the chat or the Q&A. Hopefully people didn't get scared by that really big flow thing you had going.
Oh yeah, it scares me every time I look at it.
Yeah, I thought, wow, I thought that's a lot of links there.
It's a lot of links, but it believe it or not, that helped me to write the code.
No, I sometimes you have to sort of visualize things and see how things fit together. So
the hardest part, believe it or not, is developing the notation, because the notation that exists in all of the published articles on this is terrible, and I tried to streamline it so it's hard to look at, but it's compact and general. And so,
yeah, this is maybe a little bit of a blasphemy, but I've been reading the original Falegi-Sunter paper on record linkage, and the notation there, in my opinion, is horrible.
yeah, notation is hard.
Yeah, it's not very good, but but it's really important to convey, to convey what's going on and the mathematics and the theory. So, okay, last chance for questions. Oh, somebody, I guess we have another question in the chat. Oh, yeah, so I think it was the same question. Yeah, okay, so Dimitri, are you okay with the question, or did you want to come off of mute and chat with Joe?
I think he added a clarification, Wendy, saying that I think I meant toy data.
Oh, got it. Okay.
Oh, yeah. Toy data is easy to come up with. I like to, when I'm checking my my programs, I also like to use small examples and then use them to model populations from which to then draw for simulations. So I usually model my simulations after real data, but of course you could use toy examples too. Real data tends to be more interesting because the toy examples all tend to be much better behaved than real data.
Yeah, but I think it's always good to start with, okay, something known, it's easy, it should work with that, and then go on to others. I think, Dimitri, I guess you unmuted him, Nana?
Uh-huh, I did.
Okay, go ahead. Ask Joe your question.
Hello. So I don't know the word I'm looking for, but your modeling models, they work for some situations, certain toy data, and not for other kinds of toy data, and not as well, right? It's a complicated question. I'm sorry. I'm not sure I have the terminology for it. I guess
I didn't, because of the sound quality, I didn't hear one important word in your question. So is it, are you thinking about the types of variables that it will accept or not accept?
Yeah, I was going to try to interpret what, I think what he was saying was maybe, do you have a sense of when it doesn't work?
So it can describe a joint distribution arbitrarily well if you just give it enough classes. So there is really no categorical data situation that it can't handle. I am less familiar with non-categorical distribution. So for example, I've been playing around with count data, like the number of tracts in a county. So that is a very long-tailed count distribution, or that has much longer tail than a Poisson, say, but it can be modeled as a mixture of Poissons. And so you throw that in the model, you treat it as Poisson, you do get a reasonable number of classes, but still the classes might still proliferate too quickly if that Poisson distribution has a short tail, and it does. So, so you might want to go to a negative binomial, which is more complicated. So the short answer is, if you're willing to play around with the component distributions that go into this and implement them, you can pretty much describe any amount of associations, any associations of arbitrary complexity in a multivariate data set, and it will pick them out if they're there. You just have to make sure that you give it enough classes for it to capture those associations. And another thing is, I didn't talk about this, but you also need to pay attention to multiple modes, because all of these likelihood functions are highly multimodal. They're very spiky. And if you're not careful, you can get caught in a bad fitting mode and never get out of it when you're running Markov chain Monte Carlo. So that's some of the caveats that I didn't have time to talk about today. But the random start values and looking for different modes and then starting from what looks like a mode that really fits the data well is kind of essential to get a good imputation model.
Great, thank you. And he asked a follow-on question. Would you recommend using this for continuous data? I tend to think I'm sort of also in the continuous realm usually.
Yeah, you very well could. I have not put that in yet, but it's almost trivial. The way you do it is you just say, the easiest way is to say, well, every latent class, so variable, every latent class has its own mean, but then you have a pool, you put in a common variance across the classes. If you don't do that, you run into some sticky identification problems. And what happens is you get a situation where where single observations go into their own class, and you don't want that. So if you pool the variances, the pooled variance model, that's almost trivial to implement, and I just haven't done that yet. But yes, the short answer is yes, that can be done. I haven't done it yet, but that's coming soon.
That's fantastic. Good. All right. Well, thank you. Great discussion. I'm glad we had some questions, and thank you again, Joe, for coming here again and giving this presentation, and for all of your hard work and for your support for open source. So,
sure. And so stay tuned, and hopefully before too long, I'll have a version of this package that I can distribute to people. So
great. That would be fantastic. All right. Okay. Well, thanks again. Appreciate it. And yeah, don't forget July Govys link. And should be a good presentation. All right. Take care. Thanks, everybody.
Thank you.
Thanks again,
Bye.
Joe.
Bye, everyone.
Bye.